In this video, we're going to discuss the forward Euler method. So recall from the notes that the forward Euler method involves obtaining the approximation to the solution at time step n plus 1 as a sum of the solution at the time step previous at time step n plus delta t times the forcing function evaluated at that previous time step n. So here we're going to show graphically what exactly this means. Remember first that we're solving the first order ODE, u sub t equals f of u and t, and we're giving some initial condition at time 0, u of 0 is equal to some number u0. Okay, so what we're looking for is a set of ordered pairs of tn's and vn's, and that makes up our numerical solution. So let's see what happens. At time step n equals 0, we have already that v0 is equal to u0. That's the given information from the problem. Now, how do we get to v1? Well, we have here the method telling us if we substitute in n equals 0, we end up with v1 is equal to v0 plus delta t times f of v0 and t0, which is 0. Okay, let's see what this means graphically. So I'm going to make a plot here of our numerical solution versus time. Okay, also consider plotting here on the y-axis the real solution u of t. So we start here at time 0 at the given value v0, and now we want to find what is our approximation at t is equal to delta t. Delta t, remember, is this distance here. It's the time step. So somewhere along this vertical dotted line is going to be v1. But how do we get there from v0? Well, you can see here that f tells us the time derivative of the solution. So if I take the time derivative and multiply it by delta t, then I move delta t in the direction of that slope. So f of ut is the gradient, or the time derivative, at this point. So let's suppose, for example, that this line has a slope f of v0 and 0. Okay, so this slope tells us the time derivative of the solution at this point. Now for the forward Euler method, we just follow this time derivative a distance delta t, and once we hit this point delta t forward in time, we've arrived at our next numerical point, v1. So now we have, as part of our numerical solution, t0 and v0 to start with. Remember, that was 0 and the given v0. And now we also have t1 and v1, and that's delta t and v0 plus delta t times f of v0 and 0. And this process continues. So now if I want to move another delta t, that brings me to t equals 2 delta t. I need to evaluate the slope now at time step 1. This is t1. So let's suppose now the slope looks like this. So the slope here is f of v1 and t1. And now I just follow this slope all the way over to 2 delta t, and I end up at their next numerical point. This is v2. And this process continues as far as you like.